Hi everyone. Today I'm honored to have this opportunity to present my work. My topic is an adaptive X-vector model for text-independent speaker verification. This presentation will consist of 4 parts. Now let's begin. My research is on speaker verification. Typically, they consist of a front end and a back end. The front end is used to extract low-dimensional speaker embedding, such as I vector and X vector, while the back end, such as PLDA, is used to measure the similarity between speaker models and the test utterances. For the past decade, most popular SV methods have been based on I vectors with a PLDA backend. Recently, more attention has been given to deep speaker embedding learning methods. Some methods use DNN to combine with ASR to enhance the modeling of the I vectors, and some others directly discriminate between speakers, like TDNN, CNN, LSTM, and so on. Speech signals are easily corrupted by various factors such as emotion, channels, and environment noise. How to extract robust speaker embeddings is one of the principal interests of SV. Data augmentation technique is the most straightforward way to solve this problem. The citizens can achieve better performance while constructing additional training samples using expert knowledge or extra data sources. Another choice is applying the adversarial training strategy in the speaker characteristics modeling process. Through weakening the ability of discriminating the environment types, SNR, or other relative information in a speech, the speaker embedding extractor generates more robust speaker representations. Different from the above-mentioned methods, we investigate the adaptive learning methods for robust embedding extraction, which adapts models to the acoustic variability arising from various factors, such as channel and environment noises. The ACNN and ABN are employed in the frame-level layers. By dynamically generating the parameters in models, they have more flexibility in capturing speaker information. In this section, I will outline our proposed algorithm. Let us begin by looking at a typical X-vector SV system. It includes frame-level and utterance-level parts. The frame-level part consists of several TDN layers, which deal with the local short context information. As we know, the TDN layers could be implemented as one-dimensional convolutional neural networks, where the filters slide along the time axis. A pooling layer and several fully connected layers are followed to get low-dimensional speaker embeddings in the utterance-level part. Next, we will introduce our proposed methods. First, we will introduce adaptive convolutional neural network. Figure 2 shows the overall architecture of our ACNN. During the first step, the attention mechanism is applied, and the value vectors and the attention weights are calculated. Then, we generate a context vector by leveraging the statistical information inherent in the weighted value vectors. After getting the context vector, we can generate the convolutional parameters by a linear combination of components from a parameter pool. The component filters can also be trained through a typical backpropagation algorithm Finally, once we obtain the weights and bias, a convolutional convolution operation is applied to the inputs. Next, we will introduce the adaptive batch normalization. The main difference between the ABN and the BN is that the scaling and the shifting parameters are dynamically generated for different inputs in the ABN, while they are fixed for all the inputs in the BN during testing. First, the weighted context vector can be calculated with the attention mechanism. Then, the scaling and the shifting parameters are generated from the context vector using fully connected layers separately. Finally, standard batch normalization is employed with the generated parameters. Okay, we have shared our technique. Now, let's begin to show our results of experiments and analyze them. First, I should clarify the datasets used in our experiments. The WorkSetup database, including the WorkSetup1 and the WorkSetup2, is used for training. Since a few speakers are included in both the SITW and the WorkSetup datasets, these speakers are removed from the training dataset. All experiments are conducted on the SITW and voices datasets. In order to increase diversity in channels, environmental noise, and so on, the data augmentation techniques, including adding noise and reverberation data, are applied to make our proposed methods work better. We mainly tested 5 different systems. The first system is our baseline system. The systems marked as ACNN and ABN are the systems applying 2 kinds of proposed methods separately. The last but one is a system applying both ACNN and ABN adaptive methods. Finally, we report the results using the score fusion of the ACNN and the ABN system with equal weights, which is marked as fusion. There are our main results. Table 1 presents the results of different systems on the SITW and the voices datasets. It can be observed that the system applying either the ACNN or ABN outperformed the X-vector baseline system. On the SITW dataset, these 2 systems can both improve the baseline by about 15% for all evaluation metrics. For the voices dataset, the ACNN achieves at most 21% relative improvements over the baseline in terms of mean DCF and act DCF, while the ABN achieves at most 17 relative improvements in terms of EER. The combination of ACNN and ABN can obtain some further performance improvement over the ACNN and ABN systems, especially on the SITW dataset. Among all of the above systems, the fused system achieves the best performance, especially in terms of the ACT-DCF, which improves over the baseline by nearly 38% and 29% on the development set and the evaluation set of voices, respectively. The hyperparameter M controls the number of component filters. The experimental results with different N are listed in Table 2. There is a larger gap between the development set and the evaluation set when N equals 2. This means that too few component filters cannot guarantee the generalizability of the model. Generally, the speed system where n equals 4 achieves the best performance. Therefore, n is set to 4 in our experiments. To test the effectiveness of the proposed ACNN and ABN in different speech environments, we select clean utterances and degraded utterances from the SATW dataset to simulate different conditions. The results in Table 3 and 4 show that both the ABN and the ACNN achieve significant improvements under all conditions. This comparison demonstrates that the proposed algorithms are robust to environment types and speech quality. My presentation is coming to an end. Now I will conclude our work. In this study, we employ adaptive mechanisms in the DNA embedding system to adaptively utilize the information of inputs. More specifically, the ACNN is introduced into the frame-level layers. Such a mechanism helps to obtain more expressive features. Furthermore, the batch normalization layer is enhanced by dynamically generating the shifting and scaling parameters. The proposed two methods have obvious complementarity with each other, especially at the score level. My presentation is finished. Thank you for your attention.